Right, a quick hello to everyone who's signed in at the moment. We're just waiting at the moment for other people to join, and then we'll be starting in a couple of minutes' time. So if you just hold on, and we will start at 3 o'clock BST. Right, hi to everybody who's here now. There's still more joining as I'm talking, but we've got a lot to get through. So at the moment, I need to start now, and people will have to join in. Thank you for all coming. And today, slight change of plan. We were giving the talk with another company, but it all went a bit pear-shaped yesterday. So I've had to complete the presentation with just me. Today, we're talking about mapping a route to protection. A protection from what? Well, a protection from fire or explosion that occur within your factories. Now, the most important thing to remember is, you've been doing this for 25 years, 30 years, never have an explosion. Why should you worry about it now? It's not going to happen. Um, I compare this to wearing a seatbelt. Every day of your life, you get in your car, you put on your seatbelt automatically. And it's not because every day you have an accident, it's to cover you for the day that you might have an accident. And if you do have that accident, you're very, very pleased that you wore your seatbelt. So let's move on. Talk a little bit about Sigma-HSE now. We're a group of company, our headquarters are in the UK, and we're dedicated to the provision of health, safety and environment to the industry. Our main office is Sigma-HSE in the UK. We've got units in India and units in America dealing with it. Our areas of expertise, well, we bring together our UK, Indian and USA experts to provide our clients with a global HSE service. And this can also result in cost-effective engineering solutions. We undertake laboratory testing in our UK laboratories to ISO standards. You can use ASTM standards, BS standards, etc. We can do consultancy, testing, or training. The Sigma HSE group have technically highly qualified engineers, scientists, and chemists. They're experienced professionals, and some sit on standard committees. We work in a global industry, so we work with companies that are not just based in the UK, but are based worldwide. And we try to resolve not only your local, but also your global problems. We work in diverse sections such as pharma, food, chemicals, oil and gas, utilities, personal healthcare, and the list goes on. We can do dust, gas and vapor, fire and explosion testing in our laboratories here in the UK. And we've got a small dust testing laboratory based in India. We can provide electrostatic solutions and testing. Chemical reaction hazards laboratory, we recently set up about a year ago, and now we can do all the chemical reaction hazards laboratory testing for you. Things like DSC, ARSST, ARC, Carious tube, anything like that we can do for you now. We work with ISO EN 17025 compliance, and we are the only laboratory in the UK that have that level of certification. Our consultancy team provide a wide range of specialist technical knowledge, and we cover industrial fire and explosion hazards. In the UK, it's DESIR. If we look at Europe, we would look under the ATEX directives. We can look at electrostatic problems and provide solutions for them, along with our testing laboratory to check out that your materials are whether they're insulating, conducting, or problematic. We can do PHAs, QRAs, hazards, HAZOPs, PSM, etc. And functional safeties such as safety integrated levels, layer of protection analysis. We can also do DEERS calculations for looking at vent sizing packages under CRH problems. And we offer training workshops. This is one of them, doing the webinars that we provide. So first steps on the map. Well, before you go anywhere, you have to develop a basis of safety. The idea of this is to log everything that you can find and decide which route you're going to take along the road. The basis of safety data, such as on MIE, LIT, MIT, KST, PMAX, etc. And these things we will look into as we're going along. Also, always what type of equipment are you using? Is it a mill? Is it a silo? Is it a mixer? Is it just gravity fed? Do you store the material? Do you heat it? What type of equipment do you use? Is it ATEX certified? Is it old material, old equipment that maybe you really need to get assessed to make sure it can remain in operation in the zone area that it's placed in? Operational and mechanical procedures. These must always be supplied by the company so that people understand how the systems work, and you must work within those operational and mechanical procedures. If you go outside of these operations, you need to log it and report it. But these procedures have to be checked and maintained on a regular basis so that you ensure that any changes you make are kept up to date. Deviation from normal operating conditions or processes. This can happen for many reasons. Sometimes someone wants the production to be quicker. Sometimes they think if they increase the temperature or the pressure, you're going to end up with a better result. A piece of equipment may go down and you put a different piece of equipment in its place. Similar, but not the same. You have to take this into consideration when you're building your basis of safety to make sure that everything is safe during your manufacturing process. Human factors. Well, I could go on forever on this one. Sometimes humans are brilliant. Sometimes they can smell something, they can hear something, they just sense it. If someone's been working with a piece of equipment for 20 years, they get to know all the rattles and bangs with it. If they find something is not quite right, they need to report it. On the other hand, human factors are the worst thing you can ever have. They can not only do absolutely stupid things, but they can actually repeat those stupid things over and over again without thought of the consequences. So you need to look to see how much effect these have when you're looking at your processes. Material properties. When you're looking at material properties, you have to say to yourself, why do I need these? I've got a safety data sheet, which I'll go over in a minute, and it doesn't say there's any problem here. All it says is some obscure wording of this may cause an explosion hazard, but it doesn't tell you why or what's wrong with the material. But many of these properties are not on safety data sheets, even though they should be. So if you're working on a specific basis of safety, you need the correct material property to be able to ensure you can work. If you don't know at what discharge energy your material can ignite at, how can you look at the electrostatic problems that you're working with? If you don't know the severity of the explosion, how can you fit the right explosion vent panel? So it's very important that material properties are obtained and a full list kept for your processes. whether or not you believe they're dangerous. The risk level and tolerance that you can work with. If you're working in an area on a greenfield site, then maybe you think to yourself, you know what, I don't care if the explosion vent panels go off every day, there's no one here but the people working on the factory to listen to it. On the other hand, if you're in a built up area and it happens, you're going to get a lot of telephone conversations about what's going on in your factory. So how much tolerance can you give it? And what sort of risk level are you willing to work with? I suggest you work with a lower risk as possible. And there's many more things that you can take into consideration, depending on the materials you're working with, which may have environmental problems, or the type of process you're working with. It could be extremely high pressure, extremely high temperature. So we've had a look at these items, and there's three types of basis of safety for fire and explosion risks. One is explosion prevention, basically avoid the flammable atmospheres. One is avoidance of ignition sources, avoid the sufficient energy to ignite an explosion. We've got explosion protection, basically reduce the damage done to plant and make sure employees are safe from explosions. So what are the conditions for a dust explosion? Well, firstly, the dust must be flammable or combustible, and it must be airborne to form a cloud. Concentration must be within the explosion limits. There's no upper limit for dusts, but it must be above the minimum explosive concentration. The particle size distribution should be capable of propagating flame. Anything above 500 micron is debatable whether it would actually explode. The atmosphere, oxygen, needs to support combustion. Must have sufficient energetic ignition source. So if your material has an MIE of 50 millijoules and you have a spark of 3 millijoules, then it won't ignite it. So we've got the fuel, we've got the oxidant, and we've got the ignition source. The fire triangle. What can create a fire? What can create an explosion though? Mixing the oxidant and the fuel together, not having them separate. Confinement. In order to get an explosion, you must confine it, and then it can build pressure up and blow out. If you've ever lit gunpowder outside on its own in the air, as you see by the cowboy movies, it fizzles and bangs. Confine it, and you're in a different kettle of fish. So why is it so important to get flammability data? Well, you're required to understand the explosive properties of your materials. You're required to understand the sensitivity of materials to potential ignition sources, hot surfaces. You may have electrostatic sparks or mechanical sparks. Helps you determine whether you can stay outside the flammable limits or not. And actually now, it's a legal requirement on all EU safety data sheets. This came into effect in 2021. So make sure you're using the most up-to-date safety data sheet and check to make sure it's got the components on there. If it hasn't, get back to the supplier and inform them of their duty. Testing can be split into three sections, similar to the basis of safety. You want to be able to prove explosion prevention or prove avoidance of ignition sources or prove explosion protection if none of the others are available. So the EU safety data sheet changes, Annex 2 of REACH, concerning the compilation of safety data sheets from the 1st of January 2021, it is a legal requirement to include data such as MIT, LIT, MIT, Pmax, KST, the lower and upper explosion limits, or the MEC for dusts, and if you're liquids, flashpoint, and AIT. I sat on one of the committees who were talking about the Americans want to bring this in. And the interesting thing is nobody on that committee understood anything about dust explosions. I had to give a half an hour to 3/4 of an hour presentation and show the effects of the dust explosion and what it can do. Also pointing out that it is a safety data sheet. Therefore, powders should be covered the same as liquids. Gratefully, in 2021, this became a legal requirement. So for powders and dust, we've got minimum ignition energy, minimum ignition temperature, layer ignition temperature, maximum explosion pressure, dust constant, KST, dust class for explosion protection, minimum explosive concentration, limiting oxygen concentration if you're thinking of inerting, burning behavior, looking at the fire risk, often not tested by people, but I suggest you always try to consider it. Resistivity, electrostatic issues, same as charge relaxation time. If you're drying or heating or storing, ignition risk from thermal decomposition is always something you should consider. So let's look at explosion prevention. You start off with a Group A-B classification test. We show a vertical tube here now, but often now we do it in a 20-litre sphere and we see if we get an ignition or not. The idea is combustible, then you will get an explosion and a rate of pressure rise. Non-combustible, Group B, then you don't have to worry about ATEX or desir. But you also always consider, can it thermally decompose and provide a massive ignition source for other materials. So limiting oxygen concentration. It's the minimum allowable concentration of oxygen in a mixture of dispersed combustible dust, air, and an inert gas such as nitrogen, in which an explosion will not occur. Generally higher than for gases, typically 10 to 15% volume for volume. Examples are for nitrogen as the inert gas. We can do a calculation to work out the influences of gases like CO2, etc. So on the right, you can see here the different LOCs. Aluminium down there at 5, but just to let you know that a lot of people work on 5 as the lower limit when dealing with this and don't bother to test the materials. But I found several active pharmaceutical ingredients which had LOCs of 3 and 4. So please be careful, don't just guess at it. The minimum explosive concentration. Well, there's the little man looking across at a 25-watt light bulb, and he can only just see it through the dust cloud, which is a 40 grams per cubic meter cold dust cloud. I don't know who thought of this one, but at the end of the day, we've had materials, again, APIs, down to 20, 15, and 20 grams per cubic meter, and they've been flammable. So the MEC is the minimum quantity of dust dispersed in air that is required to form a flammable atmosphere. It's measured in the 20-litre sphere, and sometimes the MEC is referred to as the lower flammable limit. As I said, there is no upper limit because dust clouds, unlike gases are not homogeneous, so therefore they can bring up again another dust cloud at any time, or could have areas of dense dust cloud. So avoidance of ignition source, I'm not going to go through all of them. You've got 13 of them there. You can have a look through at the slides and pick them out, anything that needs to looking at on your site. But normally we look at the highlighted ones that you're looking at there. And we're going into those in a little bit more detail. So minimum ignition energy, this is the lowest spark energy that can ignite the optimum mixture of fuel when dispersed in air. Everything has an ignition energy, but the MIE is when it's at the optimum mixture. Capacitive discharge, normally done, looks at electrostatic discharge. Inductive discharge looks at mechanical sparking. Be careful if you see a test done under VDI, that would be done under inductive discharge. And these can often be far lower energies than the pure capacitive discharge. So check your data to make sure it's been done for the purpose it's intended for. Any ignition source with an energy greater than the material's MIE is therefore capable of providing ignition to the flammable atmosphere. Some MIEs for you to look at: 100 to 300 starch, glass reinforced plastic 30 to 100, sugar 10 to 30, though very, very fine sugar can go less than 10, aluminium 3 to 10, and APIs we've had as low as 1. The minimum ignition temperature, you can see the vertical furnace here, and you drop the powder through it, you see a flame at the bottom, is the lowest surface temperature that can ignite the optimum mixture of fuel when dispersed in air. And here we go, the optimum mixture. MIT is basically the auto ignition temperature for dusts. It's used in the calculation for the maximum permitted surface temperature of equipment. For dust, there is no T rating that you get with gases and vapors. You just use the temperature. The range is from 200 degrees to 700 degrees. And we have the layer ignition temperature is the lowest surface temperature that can ignite a 5mm layer of material. Again, this is also used in combination with the MIT to determine the maximum surface temperature for equipment in hazardous areas. So the most common ignition sources: electrostatics, risk is high due to some dusts having very low MIE values. Flames and hot work, risk is high and ignition would depend upon the MIT of the dust. Hot surfaces, risk is moderate as many values of MIT and LIT are quite high, although some materials do have much lower values, such as sulfur or sulfur salts. These can be very low temperatures. Electrical sparks. All electrical equipment must be suitable for use for any given flammable dust in the prescribed zone that you have designated. Mechanical sparks. The risk of ignition is high when there are very low values for MIE and also values of MIT and LIT. To give you an idea here, there's about 40 dust explosions a year, creating injury and loss of life, plant repair, compensation, reputation, business interruption, loss of the market, and of course, the insurance is never going to be happy with you. You can see the biggest risk is mechanical, and then we've got overheating, and we have open flames, etc. coming down. Electrostatics is there, and it's fourth on the list. And it's the only one mentioned in ATEX. So, hot surfaces and temperature classes. Maximum surface temperature of the equipment of a worst case material is used. If you use multiple equipment, you must always look at the worst case. Temperature classes of equipment exist, so they can be properly specified for the application. So, for dust, limit temperature of equipment as follows. If dust clouds lightly, 2/3 of MIT. If dust layer is present, then take 75 degrees off of the LIT. And always remember the LIT is on use for about half an hour odd. So quite often this temperature is a lot lower than the MIT. Flames, smoking, and hot work. Another one there. Hot work should be controlled by a hot work permit. So this should never occur if you're working properly. Make staff aware of hazards to avoid likelihood of common ignition source problems. Smoking, thankfully today, is banned in all factories, not just in hazardous areas, and only permitted in designated areas, often located on the outskirts of the building, of the area. Often control all access to hazardous areas. People should not be just walking in and out of hazardous areas. You never know what ignition source they're bringing in. Electrical equipment. The electrical apparatus must be suitable for use in the area depending on the following. You must look at the MIT and LIT for the surface temperature. The zonal classification is it a zone 0, 1, 2, zone 20, 21, or 22. The ingress protection for the dust, you have to know what it's set at. And this will depend on the zone again. And the type of powder, is it conducting or insulating? In the instance of electrical equipment, then conducting is just as dangerous as insulating, if not more, because it can conduct material, electricity across the surface of the electrical motor. And here below we see a typical sign label on a piece of electrical equipment stating dust, the zone 2, category 2, for the dust, EX rated, type of protection. It works as a 3C piece of equipment. It has a temperature class of 80 degrees. So here you go, that's for the dusts. Electrical equipment must be installed and maintained by competent personnel, and we like to recommend complex certified people to do it. As you saw on the list of equipment, mechanical equipment is one of the biggest risks that you have. So 6 potential ignition sources by non-electrical equipment: hot surfaces, flames and hot gases, mechanically generated sparks, electrical ignition sources except stray currents, and static electricity. So all types of mechanical equipment will have these items to consider. So the equipment in the hazard areas should undergo a non-electrical equipment ignition risk assessment, short NIRA. Moving on now to static electricity. This is, as I said before, mentioned explicitly in DESIR and ATEX as one of the ignition sources to be controlled. Static is generated wherever movement takes place. Static electricity is often intrinsic to the intended process, so it's very difficult to stop it happening. You're pouring, You're flowing through pipes, people are walking, you have polycarbonate sheet round rollers, you are spraying, you are mixing or blending or spray drying, for instance. It's a very specialized topic and not to be confused with electrical problems. Sometimes people put electricians to look at electrostatic problems and they get very confused by it. So assessing static hazards, do you have a flammable atmosphere? Can you get charge generation in your process? Can you get charge accumulation? How much energy is produced? And what type of discharge mechanism would you have? Would you have a brush discharge, a spark discharge? You could have a propagating brush discharge. You need to know the quantity of energy and the type of discharge mechanism can be achieved. So discharge mechanisms, corona, we don't often worry about this. It's very minimal, non-incentive unless they develop into a spark. Brush charged insulator, 3 to 4 millijoules, only for gases and vapors. It doesn't matter of the MIE of your product. It has now been proved that brush discharges will not ignite a dust cloud. Charge isolated conductors for spark, the most common one, 0 to over 100 millijoules. Gases, vapors, dust, mists, and this will you need to look at depending on the capacitance and the voltage of your system. Cone discharges, these happen normally in short, fat, dumpy silos with granular material in, highly charged insulating powder or grains filled into a metal earth silo up to about 150 millijoules. And then the propagating brush discharge, two surfaces of a high resistivity material. They are oppositely charged and short circuit to form a propagating brush discharge up to 1 joule of energy. This will put you in hospital if this hits you. So it's one of the things you definitely don't want. And again, having someone look at your system and solve the problem with electrostatics is imperative. I have now been to plants where 3 or 4 times people have decided to do it themselves and created a situation where propagating brush occurred and blew up their equipment, which they didn't have before they started doing the changes. So beware. And of course, for static, you need to bond or earth. Bonding is the joining of discrete items of conducting plant with suitable electric cable. Many items may be bonded together, not just 2, 3, 4 can be bonded. Earthing, connect to the suitable earth point with a suitable electric cable. Bonding runs must be earthed at both ends. The reason is you can bond everything together, but it will still develop a high charge potential, and you have to discharge this, dissipate it to earth. And the earth must be continuous. Typical ground proving unit for tankers, you connect it up. If it's red, it's not working properly, you need to change the connection point. If it's green, you're okay to go. This is very quick and easy for tanker discharge to let you know that you are suitably earthed. Personnel. Ground leads can be used to ground personnel, are impractical for people who have to move about. The most common thing is to put static dissipative flooring down or mats where you're working, to have static dissipative shoes, clothing and gloves on. The total resistance between the body and ground should be less than 100 megohms. So summary avoidance of ignition source. Consider all types of ignition sources. Concentrate on the 5 most important ones: hot surfaces, flames, hot work, electrostatic discharges, mechanical, and electrical. Perform hazardous area classification. As I said, depending on the zone you're working in, 0, 1, 2 for gases, 20, 21, 22 for dusts, will decide what type of equipment, etc. you're going to have in and how much protection you need. Ensure all equipment is suitable for use in that zone. Consider more detailed assessments for such things as electrostatics, the electrics, and the mechanical. Control all naked flames and hot work by permit to work systems. Make sure you obtain flammability data, you record it, so you understand what you're dealing with. Understand if a potential source of ignition become active, and most importantly, can become effective. And all this must be written in a basis of safety report. So another one very common way of making a plant safe is explosion protection. This didn't work in Imperial Sugar in 2008. The whole of the sugar plant blew up, 14 deaths, 38 injuries, 14 with life-threatening burns. The explosion was fueled by accumulation of sugar dust, and it propagated throughout the building because they had no means of isolation and they didn't understand how a dust explosion worked. They never had anybody in to give them any advice. So, explosion protection, we use the 20-litre sphere. Picture of it there, no marks for guessing why it's called the 20-litre sphere, but it will dictate the maximum explosion pressure resulting in the optimum concentration of dust. The KST, K German for constant and Staub German for dust, the dust constant. This will not change, whereas the rate of pressure rise, dPdt, will, depending on the size of the vessel. Explosion severity data is required when explosion protection systems, venting, suppression, or containment is used to be the proposed basis of safety. And here's the standards it's conducted under. We have four classes, dust classes, ST. ST null, no explosion, such as silica. ST1, 0 to 200 bar meters per second, weak explosion. Just to let you know, the sugar explosion, which did the complete destruction of a sugar factory, was a weak explosion. Powdered milk, charcoal, sulfur, sugar, and zinc. ST2, greater than 200 and less than 300, a strong explosion. Materials such as cellulose dust, wood flour, and polymethyl acrylate, for instance. ST3, greater than 300, no upper limit. Very strong explosion, anthraquinone, metals such as aluminium and magnesium, and the biggest one I've ever come up against is aluminium lithium hydride. If you drive an electric car, that's what's sitting underneath you in the form of your battery. To give you an idea, hydrogen 550 kg, aluminium lithium hydride 1,200 kst bar meter per second, 3 times the explosion violence of hydrogen. So mitigation of risk, it states in ATEX and DESIR, if a risk cannot be eliminated or controlled, the detrimental effects must be mitigated. Reduce the number of employees exposed. Well, this should be a natural thing to do. Avoid the propagation of fires and explosions. Bear that in mind, Imperial Sugar. Explosion relief arrangements can be put in place, explosion suppression or containment. Then we have other things such as personal protection equipment. If several dangerous substances are present, then take account of the worst case. So toxicity is one of these. Safe handling, storage and transport of dangerous substances, including waste. Because it's labeled as waste in your factory, it's still the original material. It still contains their property. Therefore, be careful with the waste, because it can be just, if not more dangerous, than materials you're processing. Explosion in a closed vessel, you can see creates hot gases. The pressure will increase, and any protection system must be able to cope with the expansion and or pressure increase. The dPdt, how fast does it rise, and what is the maximum pressure that is evolved? And from the dPdt, we get the KST. So those two properties, KST and Pmax, are to be used in explosion venting suppression containment systems. So containment, isolate pieces of equipment where explosions could occur. All isolated plant to withstand overpressure. Good points, no release of the combustion products or toxics. No requirement for safe areas. Bad points. The equipment is expensive to build and maintain. It requires pressure testing and the associated documentation. The equipment can also be very heavy. All parts of the plant must be made strong, including connecting pipes, ducts, flanges, covers, must be able to withstand the maximum pressure expected and must be over its lifetime. So maintenance have to know why you have 27 bolts on the plate, the sealing plate, instead of just 6. 6 would seal it. 27 are there in case there's an explosion. Explosion pressure resistant or explosion shock resistant. Strong plant is expensive to build and can be difficult to operate. Venting, probably the most common here of explosion protection, protects plant and personnel from the effects of an explosion. There's a controlled release of pressure for a weak or open section, and the vent sizing used dictated from the KST dPdt data in the 20-litre sphere combined with the Pmax. Gives the ability to control release locations. Must be in a safe place, not facing the building, not facing where people walk. I've seen them outside a canteen where people queue to get their food, and they're 2 meters above the ground. They can be retrofitted to weak equipment. The bad news is combustion products and overpressure is released. Non-flammable systems lead to explosion propagation. Non-flameless systems lead to explosion propagation. So advantages can be designed in-house, relatively cheap to vent, needs little maintenance, but be careful of that, very wide range of applications. Disadvantages, material is released, unsuitable for toxics, corrosives, must discharge outside the building to a safe area. Again, another relief panel vented to where the managing director of the company parked his car. After being explained what would happen, he parked his car down the other end of the car park and walked into his office. Restrict sighting of plant items, because if you're going to vent a piece of plant, then you need it on an outside wall. And large safe areas are required. People are going over today sometimes to flameless venting. These are special devices attached to the explosion vent so they can stop flame while allowing venting to go on, the Q or the flame quench. The efficiency is reduced compared to a bursting disc, for instance, and they need to be type tested. The flame is prevented from exiting the vent. High pressure and smoke can still fill the workplace. So be careful. You're still going to get gases coming out, and hot gases probably under pressure with smoke accompanying them. So it must be recited in a restricted area. I've seen one instance where it was facing a lift. Very useful if it goes off when the door opens. Requires regular maintenance. And if you're using materials such as sugars that can caramelize, then make sure these vents are cleaned at regular intervals and check to see they are functioning properly. Must be suitable for materials being processed, such as toxics, caramelization in sugar, for instance. Explosion relief doors. I've seen them quite often around. They're quite often rusty and badly maintained. Don't require replacement after an explosion. The door opens, lets the explosion out, and you're safe. They're easy to maintain and cheap to fit, but very often neglected in your maintenance regimes. Cons, well, prevent door closing too quickly after an explosion, and I'll show you a picture of that. They can weather badly and therefore robustness could be compromised, and often, as I said before, a failure to maintain. This is what happens when the door closes too fast. You get a vacuum forming. If the vent opening closes after the explosion is venting, the hot combustion gases will cool down and create a negative pressure. You do this with a plastic container in a microwave, heat it up, then get it to cool down, and you can't get the lid off. It's the same principle. Flame propagation. Most of the fuel air mixture will be expelled from the vent and burn outside the vessel. The length of the flame can be predicted. For dust, length is 8 to 10 times V over a third. Well, if you're no good at maths, just take the vessel size as being 1 cubic meter. Then V's 10 meters long. That's how long the flame will be coming out of your vent. But it will not reach further than 60 meters. For gases, it's 5 times V to a third. The width's difficult to predict, but with the EN standards, they have a formula for dusts. Typical vent problems, leaking and badly maintained vent here. Outside, high up in the building, no one bothers with it. The vent is leaking. It's got other things, can have rust on it or corrosion on the aluminium. And because it's so high up, no one bothers with it. Water could be dripping in occasionally. So what do? Put a piece of plywood on top, cover it with plastic and heavy weights. These will be missiles when the vent opens, and it could even prevent the vent opening, which could blow up your vessel and injure people inside. Explosion suppression. Extinguish the explosion in the early stages. Injection of pressurized suppression agent at a given pressure. So when it detects a rapid rise in pressure, it will reach a pressure and then open the suppression bottles, you can see there, the red one, and fire inert suppressant into the system. So the good points, no external effects of explosions are experienced. And they're very suitable for toxic corrosive materials. The bad points, they're reliant on effective explosion detection. They're a highly specialized design, and you will lose all of your product in that vessel after the inertion has entered the vessel. So explosion suppression, what are the advantages? No release of the materials, suitable for toxics, corrosives, nasty materials of all types. You don't have to worry about where the plant is located. They can be in the middle of the plant, on the outside walls, up on a mezzanine, down on the bottom floor. There's no flame propagation, so there's no area that you have to isolate. and make a restricted area. A well-designed system must incorporate isolation measures, so the explosion starts in the vessel and gets extinguished in the vessel. They've got a few disadvantages, often high capital cost when compared to venting systems alone. They need regular maintenance by the installation company. They only work when operational. After activation, recharging of the bottles is necessary. And as I said before, of course, you get a total loss of product. So if we look here, you'll see the suppression bottles on a fluid bed dryer. Again, they're situated to be able to detect the explosion quickly and to fire any suppressant into the system so that it can cover all areas of the vessel. So if you look at the dust collector, for instance, you will see multiple injection points. So you will see them on the dirty side and often on the clean side of the filter, for instance. And the same goes for the fluid bed dryer. You can see them, if you look at them in real life, you may see 2, 3, 4, even 5 on a large fluid bed dryer, for instance, to ensure that you cover all areas of the vessel and extinguish anything that's happening. Isolation. This is necessary to prevent pressure piling effects and flame jet ignition. Without isolation, the explosion in secondary vessels could be more severe than what the design and criteria is, and there's a risk of a secondary explosion. Again, isolation, absolutely critical. You only have to look at the Imperial Sugar explosion to see what can happen if you don't isolate. Types of isolation: rotary valves, fast closing valves. So summary of explosion protection: determine flammability characteristics of the material, Pmax, KST. Review STS to see if materials are hazardous, toxic. Review hazardous area classification so you can identify the equipment location. Venting and suppression systems need to be designed and installed correctly, as should fire protection. For containment, the vessel needs to be certified for use at expected pressure, and maintenance needs to be by trained people. Location may be a problem for venting. Confirm suitable isolation. Assess special precautions, hot work permits, management of change, permit to work, etc. Personnel working in hazardous areas should also be suitably trained. So overview of a mapping route. Use a combination of measures relied upon to ensure safety. Highlight aspects of the design and operation that are safety critical. Many items to consider. You need to look at equipment, procedures, deviations, human factors, material properties, level of acceptable risk, etc. For fires and explosions, normally you've got 3 ways to go on this map: explosion prevention, avoidance of ignition sources, or explosion protection. Explosion prevention, several ways to achieve this: change the material, not often a choice; remove the oxygen; work outside the flammable range for gases and vapors. Not really possible for dusts, as powders are not homogeneous. So there's some of the things you need to look at for explosion prevention. Avoidance of ignition sources to prevent the ignition. All ignition sources need to be considered. I showed you 13 of them taken from EN 1127. Normally the most common of the 5 we talked about. These would be hot surfaces, naked flames, hot work and fires, electrical equipment which is poorly installed and maintained, and cabling. I've seen chocolate box connectors in zone 0 areas connected to ATEX certified electrical equipment. So they've bought the equipment and had it installed by a pretty poor electrician. So make sure it's not just your equipment, but it's the wiring of it and the installation of it that should be complex trained electricians. Electrostatic discharges. Have a look to see if they're possible to generate electrostatic charge and accumulate it. What type of discharge could be possible? Do you have enough energy to ignite the materials? Mechanical sparking, unsuitable mechanical equipment, quite a common thing we find when we're walking around, especially with old equipment. Get your NERA done and then you can know that you're safe. I've pointed out to people that they've had friction sparks going on inside their equipment because you can see where the blades are rubbing against the sides. They never knew this, they never observed it on maintenance. So please get it checked. Material properties. As I said before, how can you use avoidance of ignition sources if you don't know how it can be ignited? So MIE, electrostatic and mechanical ignition, may be also necessary to look at electrostatic properties, such as power to volume resistivity. Is it insulating or conducting material? We talked about conducting materials for electrical equipment. Charge relaxation time. How long does it take to dissipate its charge? The longest I've seen is an API in an earth vessel after 28 days hadn't lost any charge at all. Or chargeability. What makes it charge the most? Is it the material it's going through, such as plastic, glass, stainless steel? Is the material conductive, static, dissipative, or insulating? The minimum ignition temperature. You can look at mechanical ignition and hot surfaces. Lower ignition temperature. Consider hot surfaces, electrical equipment, for instance. 20-liter sphere test, Pmax KST, explosion protection, containment, suppression, and vents. Limiting oxygen concentration. If you're using inerting, you need to know what value you're going down to make sure you're safe. Don't guess at it. Get the value and you'll know how far away you are. So summary, hazardous area classification, potential ignition sources. If required, do an electrostatic audit, a complete electrostatic audit, checking out earth leads. I found many earth leads, flying earth leads in particular, say on gas truck recharging points where they're not even connected and no one has checked them. If the MIEs seem to be low for dust or gases or vapors, this is a must. Look at the equipment specifications and its suitability for use. Check your operating procedures. Do your risk assessments and write them down. Material flammability, electrostatic, thermal instability properties, and again, record them. With the hazardous area classification, do the drawings, and it must be with a comprehensive report. Assess processes to understand manufacturing hazards during the charging and discharge mixing operations, for instance. Process maintenance procedures such as hot work permits, management of change, permit to work. Personnel working in hazardous areas should be correctly trained and determine what basis of safety can be used and confirm that is suitable once all information has been analysed. That's the end of the presentation. I hope you found it useful. If you have any queries, then get back to us and someone will get back to you on an email and let you know the answer. So thank you very much for attending and listening.